cadence is cumbersome. After you solve by hand a few times, here is the only polynomial. You may get third order polynomials, and then you'll say, okay, I really need the computer program to solve that for you. So you would appreciate having SPICE available. Okay, all right. So this is an example, and we talked about these current, if you plot it, versus VGS for fixed VDS, okay, you will have this quadratic curve. Oh, let's get back to one thing I want to mention here. So for these families of curves, the boundary here, okay, this boundary, dotted line, looks like a parabolic curve. Is it a parabolic curve? Do we know it's a parabolic curve? It looks like a parabolic curve. It is a parabolic curve because we know this is V overdrive, and this current is 1/2 Kn V overdrive square. And here is a different overdrive value, and the current is still overdrive square. So this is indeed a perfect parabolic curve for this mathematical model. Okay. All right. So now that you've done a few exercises, so you're more comfortable with the transistors now. So that's same circuit we have just worked on, okay? And we solved basically a few values around here. These are almost similar values that we had solved earlier. And if we use it as an amplifier, we will have a DC circuit, okay? So this produces a bias, and we will add our signal. Signal is usually AC. Superimposed, meaning in series with the DC bias. And this output voltage, now instead of having a DC value, if we wiggle our voltage, okay, in terms of VGS, our VDS will have a change, corresponding change. So this is an amplifier. So basically, the gain is kind of like the slope of this curve, because this is transfer curve. This is output versus input. So the gain is basically the slope. So slope will be equal to the gain. Okay, and the slope is negative, meaning this is an inverting amplifier. It is an AC. When your voltage decrease, your output voltage actually increase. So they are 180 degrees out of phase. Okay, all right. We're going to revisit these problems later using kind of more systematic approach. So this circuit is kind of the simplest circuit. If I give you a transistor circuit, it cannot be any simpler than this, okay? So when you see this circuit, you should be happy. This is a very easy circuit. Okay, here is another circuit that's very easy. So if we don't apply an independent voltage to the gate, we simply connect it to the drain. So we produce this kind of artificial two-terminal device. The third terminal is tied to drain. So it's like a diode. So we often call this connection diode-connected transistor. Okay, and this transistor is very easy to see. It's always in saturation. So this is always in saturation, right? Why? Because VGS is equal to VDS, and V overdrive is equal to VGS minus VTN. For NMOS, this usually is a positive number. Okay, so this means VDS As a result, VDS is always greater than V overdrive. So this transistor is always in saturation. And if it is in saturation, you can calculate the current easily. So this is 1/2 Kn V overdrive square. Now V overdrive is simply equal to VDS minus Vn. Okay, so this is a VDS minus VTN square. Okay, so it's basically this expression here. And if we call this a diode, VDS is basically the voltage drop across these diodes. And when do we use this? We will see examples when we use this. This is actually quite commonly used in a circuit. We can insert this. When you see that, you can kind of think it is a diode. It's different from a PN junction diode. The current doesn't go up exponentially. The current goes up quadratically, so much smaller than a PN junction. But in circuits, in IC, even though the MOS transistor looks more complicated than a PN junction, it has multiple PN junctions in there, it is the simplest and smallest unit that you can use. So anytime you can use a transistor instead of a resistor, it is actually preferable, both in terms of your chip area, usually translates to better power consumption. Okay? All right. So here is a design example here. You will have plenty of cases. You say, okay, let's design an amplifier. And I will use an NMOS. So here is an NMOS single transistor amplifier. And I want the transistor to be in saturation, okay? And so, and we say, okay, we want to operate at 0.4 milliamp. So this is a requirement. Usually we start with current. Why do we start with current? Later we'll find the gain of amplifier is mostly directly related to the transistor current. So it's directly related to current. It's not proportional. We will see what kind of relationship they are. So usually we design a circuit. We want to design their current, steady state current flowing through the drain. Okay. And we can also specify, okay, what is the steady state voltage, 0.5 volt. And the transistor we have, usually these come from the technology that you are designing your circuit into. Let's say you are using transistor provided by TSMC, one of the foundry. You are using a 40 nanometer technology, so you will be given the transistor characteristics, kind of like data sheet. Usually you get a much bigger file than data sheet, but you will know what technology you are designing your circuit in. So let's say, for example, this one, I have 0.7 volts threshold voltage. My mu-n Cox is this 100 microamp per volt square. And the aspect ratio, the length and width are designable parameters. So, we say Kn. Kn is mu-n Cox times W over L. In reality, these come from your technology. This is foundry, what foundry will give you. This is dimension. Dimension is design. So this you have control over. If you want larger Kn, you just design a wider transistor. So you have Kn is a controllable parameter for you as a circuit designer. Okay, so what do you have to design? Let's assume, well, we also fix our power supply. We have decided we're going to have 0.25 volts. On top, we call VDD. At the bottom, because it's connected to source, we normally call that VSS. And in this case, it's minus 2.5 volts. And we decided at the steady state, your gate is going to have 0 volt bias. Okay, so design. How do we start with the design? Well, you start with what you know. So we say, okay, we want ID to be 0.4 milliamp. Okay, so you know the current. You know the current. You have resistor. You know what you desired steady state output of VD is. Then you can calculate what kind of resistor value you use to produce that. So we can quickly identify RD. So I take my VDD, right, and VD. This is the power supply voltage given. This is the desired design value, and this is the desired current. So I have my first resistor value here. So I need RD to be 5 kilo ohm. Okay. And next, we have the transistor. So we have the current. Then we can calculate what is the overdrive voltage. And so this is a very simple calculation because we know basically the Kn here. So we can very easily put it back and say overdrive voltage is 0.5 volt. Once we know the overdrive voltage, we know VGS is equal to V overdrive plus VTN. And VTN we say is 0.7 volt. So this is equal to 1.2 volt. So we know here is 1.2 volt. 1.2 volt here, right? And this is determined by current. We know this voltage because we know what current we want this circuit to operate in. So gate is grounded, so that means this point is minus 1.2 volt. The source is at minus 1.2 volt. And therefore, you can determine RS. You know the two-terminal voltage is between 1.2 volt and minus 2.5 volt. And you know the current, so you can determine the value of RS. There's a typo here. This should be RS. Okay. So that's a design problem. It's a reverse process from a solution analysis of the circuit. Yes?
In a real transistor, is the current going into the drain actually the current going out of the source?
Yes, all the current going to the drain has to come out from the source. There's no other terminal that usually conducts current. Even the body, we normally don't take current out from the body. Okay, there are a few more examples you can practice. This is back to analyzing a circuit. So this is a common circuit for discrete transistors. This is kind of similar to your touch sensor that you are building. So you have two resistors here. Okay, these two resistors set up VG. Okay. So this is basically a bias branch, okay? And this is the active branch. This is the active circuit that you're in series with your transistor. So in this example, we apply 10 volt to the top, and sometimes we draw a horizontal line. Sometimes we draw an arrow. Okay, it just means we apply a 10 volt battery to the top. And now this is a little bit complicated. It's very easy to find out VG. Right? It's a voltage divider because the current is equal to 0. So there's no current flowing to the gate. So it's very easy to figure out VG. VG is simply equal to the voltage divider. Okay, so VG is equal to 10 mega ohm, so this is 5 volt. It's very easy to figure that out. The next one is not so easy. Next one, we need to know what is VGS. Here, the solution basically is to figure out what is ID, like our earlier examples. So in order to figure out ID, we need to know VGS. But VGS is the voltage difference between here and VS. We don't know VS. So VS is basically the same current ID times RS. So now it's a variable. So VGS is a variable. Okay, you know the resistor value. You can substitute in. The next thing is you assume the transistor is in saturation, like we have done before. So you have this nice, simple quadratic equation. This equation contains ID here. It's a quadratic equation, so you have ID on the left, ID on the right. This gives you a second-order polynomial equation. So this is very common when you solve a transistor in saturation. You most likely will solve a quadratic equation. Okay, and in this example, they get two solutions. Okay, two solutions. You substitute them in. The larger one here, for example, you substitute them in. You get VGS is negative. Negative, well, the transistor is in cutoff, so it's inconsistent. So that means this is a wrong solution. Let's try out the other current. The other current, you put it in, you get VGS equal to 2 volt. So that's reasonable for NMOS. And you figure out your overdrive voltage, that's 1 volt. And you need to verify your drain, VDS. So you know the current, you can calculate VDS. So VDS here is 4 volts. So it's the same procedure as we have done before. So we have done self-consistent solution. This transistor is indeed in saturation. Okay. This kind of bias that you see for transistor, this is for resistor, this is called 4-resistor biasing circuit, is very common for discrete circuits, like the one you're doing in lab 4. It's much less common in integrated circuits. So as we move on, you will see the entire amplifier. You don't see any resistor at all. That will be more commonly used for integrated circuit. Questions here? Okay, so we've done lots of exercise. We have not talked about PMOS. We just say it's exactly equivalent to NMOS, except current flows from source to drain. So this is a common symbol we use for PMOS. We usually draw source on top and drain at the bottom. Unlike NMOS, we usually draw it opposite. So we usually have drain on top, source at the bottom. Okay. And how do you kind of remember this? Well, you can kind of think CMOS. CMOS consists of basically PMOS on top, NMOS at the bottom. So this is a CMOS. This is a CMOS inverter. Okay, so you have PMOS usually on top, NMOS at the bottom, and on top the source is also on top. The current follows exactly the arrows in this case. So current flows in this direction. All right, and in the physical device, you will have P plus source, P plus doped drain, and you will have N-type silicon body, okay? And you will have a gate. And when the gate is biased in kind of in the negative direction, eventually you will induce a channel of holes. When there's a channel of holes, again, when you apply a bias between source and drain, a current will conduct. But since the current carrier is hole, so current flow is the same direction as the hole carrier flow. So carrier flow from source to drain. Okay, and so it's exactly consistent with the symbol here. Now, if we use our normal symbol for IV curve, we will have VDS, we'll have IDS versus VDS. IDS means current flowing from D to S. So that would be the convention for IDS. It's flowing up. So current is flowing down. So the value of the current, if you plot IDS, is negative. And likewise, the voltage is usually higher for source than drain. So if you plot VDS, which is equal to VD minus VS, is again a negative value. So for PMOS, the IV curve is in the third quadrant. Both VDS and IDS are negative, okay? And sometimes it's cumbersome to keep track of whether it's negative or positive. I would normally do the following way, okay? I would just use absolute sign, okay? In this case, PMOS will look like NMOS, okay? And I just remember in the circuit, the current is going to flow from top to bottom. And I'm going to have source on top, close to my most positive power supply, and drain closer to my most negative power supply value. Current is just going to flow downward. And the voltage, VGS, so VDS, well, I'm just going to count this voltage drop, okay? It's really VSD. So sometimes people write it as VSD, which is a positive value. You can write it as ISD, which is a positive value, or you can use absolute sign. The current voltage equation is in the model identical to the NMOS if you take absolute sign. So I can write ID really is the current flowing down in this direction, okay? It's equal to this value, which now you can call that Kp. You know, it's the counterpart of Kn. Everything is the same except you use the mobility of the holes rather than mobility of electrons. And you have exactly the same equation. It's overdrive voltage, VDS, and VDS. So you can keep track of the sign by two ways. One, you write everything by VSD. The other direction, you take everything by absolute sign, including the overdrive voltage. Overdrive voltage, the VSG, well, you just kind of ignore the sign. VTP is usually negative. VTP is usually minus some volt, let's say minus 1 volt. VTP is usually a negative number, okay? And, but you take absolute sign, absolute value, you substitute it in, you use essentially kind of a familiar equation that we use. In saturation, you have V overdrive square. In triad region, you have this parabolic curve, okay? You just have to remind yourself, PMOS, source is at a higher potential than drain, and current flowing down. Draw a circuit diagram that will help remind yourself, and then everything else is kind of straightforward. Okay, any questions? Yeah?
So can we just consider that after taking the absolute value, PMOS is exactly the same as NMOS?
Mathematical model. Mathematical model is the same. So here is the first question for you. As a circuit designer, I would actually produce a layout. Your cadence is much more powerful package than you use it for. You just use it for SPICE simulation. It is used for circuit design that actually produce transistors, circuits as complex as millions of transistors and tape out to have that fabricated into a real circuit. So cadence, you draw a layout, actually give you the physical size of each transistor. And usually you'll find PMOS to be about 3 times wider than NMOS. And why is PMOS usually wider than NMOS in their physical size? Doping concentration? Mobility? Yes. The mobility is 3 times. Electron mobility is 3 times higher. So the current, in order for them to have the same current, again, most of circuit you are going to see later kind of have this generic trend of having a stacked PMOS on top of NMOS. The current needs to be the same, right? So to have them roughly the same overdrive voltage, you match their mobility by size. So the product of mobility and size, you match them, then their overdrive voltage is about symmetric. Okay, that makes your circuit easier. So we have just one example for PMOS, okay? And let's trace this example here. So PMOS, this is a design problem. So again, recall that S source is indeed on top, drain is at the bottom, okay? And we want to design it such that 0.5 milliamp steady state current flow through it. And we want the bias voltage at drain to be 3 volt. This transistor M has threshold voltage. I mentioned PMOS usually is negative, so minus 1 volt. Kp, so it's this factor, is 1 milliamp per volt square. So the transistor size has been chosen already. And so our job is to design RG1, RG2, and RD, okay? And RD is very easy to choose. RD, we already know the current, we know the bottom bias. So the value of RD is basically 3 volt, okay? 3 minus 0 divided by 0.5 milliamp. So it is equal to 6 kilo ohm. So you find RD right away. And you can find your overdrive voltage easily because we know the current. So you substitute that in. Kp is 1 and current is 0.5. So overdrive voltage is basically 1 volt. And here I use absolute sign, okay? I know that source is always higher than drain, okay? So this avoid tracking the sign. So I know this overdrive is 1 volt, and threshold voltage is 1 volt. So I know my VGS absolute sign is 1 plus 1 is 2 volt, okay? And I look at my circuit symbol, I will say this is my Vs minus Vg, that's 2 volt. And Vs is connected to the top, we still call that VDD, even now it's actually connected to the source. So this is 5 volt, okay? So we know Vg is at 3 volt, okay? So now we have a resistor divider. We can choose arbitrary value. I can choose, so it's 3 volts. So RG2 has to be bigger than RG1, and it's roughly ratio of, it's a 60%, so 3 to 2 ratio. So I can choose RG2 to be 2 mega ohm, RG2 to be 3 mega ohm. So that will give you 3 volt. Now, this is a design problem. Any ratio you choose, you can choose RG1 to be 2 kilo ohm, RG2 to be 3 kilo ohm. That's also give you the same bias condition. So this part is totally arbitrary. So there are additional constraints that we need to think about. What constraint do we think about? How do we choose between mega ohm and kilo ohm? Less current. Less current, good or bad? Less power consumption, right. So if you use mega ohm, the current going through here is less. This current is kind of a useless current other than setting up your bias. So you do want this current to be as small as possible. The power consumption through this bias is VDD times your I bias current. So if you use mega ohm rather than kilo ohm, you reduce that by 1,000 times, okay? This current that flows through the active transistor, unfortunately, you cannot save on that. Your gain is related to your current. So if you need a certain gain, you just need to bias your transistor very hard. You cannot do anything about that. But the bias branch, you can. So mega ohm is better. Why not giga ohm? Why do we choose mega ohm? Why not giga ohm? Giga is 10 to the 9th. Mega is 10 to the 6th. So that saves even more. Yeah?
Giga ohm resistors really big.
Yes, they're really big. It's hard to get. Yes. Yes?
You get more variation too, right? It's like plus or minus percentage.
That's probably true. But percentage, you get a percentage. If you have the same percentage, that kind of cancel out. But giga ohm is hard to make, actually physically hard to make. If you are doing this, most likely you are doing it on breadboard, so discrete resistors. And you can look up DigiKey catalog. It's hard to buy giga ohm resistor. And in integrated circuits, it's also very difficult to generate giga ohm resistor. So mega ohm is kind of, mega ohm, 10 mega ohm is kind of convenient value to choose. Then you just figure out, you know, what is your VDS, whether your transistor is in the saturation region, saturation regimes. Okay. One last thing. So the current, we said in the saturation, we said it's constant. So it's actually not constant. We say this is 1/2 Kn V overdrive square. So it's independent of VDS. When we plot IDS versus VDS, it's independent. That's why it's flat. In reality, you know, as you go into saturation, if you have source and drain, this is your N plus the source, this is your N plus drain. When the pinch off point gradually move over to the source side, your effective channel actually becomes shorter. So your effective channel, so it's W over L, your channel length as your voltage increase is kind of getting a little bit shorter and shorter. So you can say, well, your current is going to become bigger and bigger due to delta L. So you can say delta L actually increase as VDS increase. So your channel is getting shorter and shorter. Phenomenologically, we just use this parameter to represent this channel length modulation. So we call this lambda channel length modulation parameter. Okay, so this is called channel length modulation. The actual channel, effective channel, gets shorter as we apply more bias on the drain. As the voltage here increase, channel decrease, the current as a result increase. But rather than having a more complicated formula, we use the same formula and just have a phenomenological linear term here. Lambda is usually a small number. So lambda is usually a small number. That's why we can kind of do this approximation. Okay? So the complete equation just become more complicated. And you kind of can see, well, you have a finite slope now. You have finite slope rather than zero slope. And it's kind of say you can extrapolate it to some kind of voltage, artificial voltage, which is equal to 1 over lambda on the negative voltage side. Now, if you include this in your DC bias solution, you'll be solving like a third order polynomial, fourth order polynomial. So by hand calculation, solving DC problems, usually you don't use this term, solving DC bias. You leave that to Cadence, leave that to Spice. Spice will automatically consider that. So normally, unless there's a case you absolutely need to consider it, DC problem within 10%, you can ignore this in DC problem, okay? In DC solution, DC bias solution. We will see on Thursday, these automatically give you an AC consideration. So AC, you cannot ignore it. You will have to consider that channel length modulation in AC solution. Okay, that will be the subject of next time, so we will stop here today. Okay.